I'm Mark Rader with IBM. In the old days, I would say installation code IBM, but we don't do that anymore. And I'm going to talk about data sharing. I've been doing data sharing since it was before data sharing, and I've had lots of interesting stories, lots of interesting experiences. As I go through this, please ask questions, and we'll, if they're not really long and detailed, I'll spend time on them, and otherwise we'll try and catch them at the end. Disclaimer, if I lie, it's not my fault. It's because I don't understand. So I'm going to start with is a brief overview of data sharing. If you are brand new to data sharing, have never heard of it before, the meat of this stuff might be a little complicated, but if you refer back to it later, hopefully that'll help. I'll talk through some of the basic configurations. There are many, many different possible configurations, but they break down into some very simple models that you start with, and I'm going to talk about each of them. And then I'm going to talk about various issues that I've seen with customers over the years and things to think about. And at the very end, I'm not going to talk about this, but there's an appendix at the back with some additional material and a few backup slides that I definitely won't have time to talk about, but which might be interesting for you to look at after the fact. So here's the simple overview, right? No, I do not have an art degree, and that's why the artwork is pretty basic. So we're going to talk about what is data sharing and the major components, the general options for configurations, and I group the common issues into three areas: performance, availability, and workload balancing. And we'll work through them. Some of them interact with each other, but that's what we're going to go talk about. So fundamentally, when I think about data sharing in parallel sysplex, I think about this as the starting point if you want to get increased availability, non-disruptive scalability, and dynamic workload balancing, right? So this is what we do in the Z space to do all these things with Db2 data. Now, I'm going to talk only about Db2, but we can do the same things with IMS data sharing, and we can do the same things with vSAM if you're using RLS, but I'm just going to talk about Db2. And then I have two definitions here, one of which I think of as a more technical definition, and one of them is more of a business definition. So on the technical side, what we're really saying with data sharing is we're going to allow applications that are running against more than one Db2 subsystem to have read-write access to the same set of data, right? So I can have it on, attached to two different Db2s on the same LPAR, or on different LPARs in the same box, or on different LPARs in different boxes, and be able to do read-write access to the data together. What I think of as the business definition is the one that I would use if I'm talking to managers or senior executives, and they say, well, what is this data sharing stuff? And I said, well, this is what gives you the highest level of availability for enterprise data that's in relational form. And if I were talking IMS and vSAM, I would use that same description. Why clients implement data sharing has changed over the years, but I've more or less grouped them here by the current drivers. So most people who talk to me today about doing data sharing are doing it for availability. They want to avoid the impact of planned and unplanned outages. They want their applications to go after data, even while they're dealing with maintenance and IPLs and things like that. Some customers are dealing with sudden changes in the amount of work that they're doing. Maybe they just acquired another company, and so the volumes have suddenly spiked. And so there are ways we can have data sharing deal with that. Another thing is dynamic workload balancing. If you have workload shifts, I worked with one customer who had European-based workload and in one environment, and North American-based workload in another environment, and the peaks were different in the two, and by putting them into data sharing, they were able to take advantage of all their processing power to address both of them using the resources they already had. When I first started doing data sharing in the mid-90s, the big reason was that we were running out of capacity, right? Our H5 water-cooled boxes were full, and if your environment was growing, you couldn't make the box any bigger. And at the time, IBM was shifting to CMOS, and if an H5 was this big, a CMOS was about this big. And so you had to lash a whole bunch of them together, and that was the only way to address the capacity constraint. Of course, now CMOS is way bigger than the H5s ever were. So I don't see very many people today saying, oh, the reason I have to do data sharing is I have a capacity problem, right? Because the hardware and the corresponding operating system has grown so big. Finally, every now and then I run across a customer who goes to data sharing to avoid doing a cold start when they run out of RBA, right? if your log RBA increases to where it's hitting Fox in the first position, you're pretty soon going to run out of gas and not be able to do anything at all. But if you take one outage and make that a data sharing member, then you can shift all your work to a brand new member with the RBA starting at 0, and you can last for much longer. So I do have worked with a couple customers doing that. And before we did data sharing, there were a number of large customers who had already had to rip apart their applications because they didn't fit in one LPAR. And they would have Db2 workload over here and Db2 workload over there that logically belonged together, but physically they had to be separated based on the capacity available in the early 90s or late 80s. And once data sharing was available, some of those customers were able to put them back together again. And so they went to data sharing to avoid the DDF overhead of these systems talking to each other. The reason why data sharing works so much is that we're protecting your application investment. When you go to data sharing, your application doesn't have to change to take advantage of it. You know, 1 + 1 still equals 2. Select asterisk works just as the same as it did before. Of course, nobody does select asterisk, right? No one? Okay, good. We have excellent scaling. Once you pay the price to go from non-data sharing to two-way data sharing, and there's a little bit of a cost there, anything beyond that is about 0.5% additional. So it scales really, really well. And finally, the applications themselves don't have to know when you go into data sharing. Now, I will make a caveat about the fact that applications don't have to change. For best performance, you may have some poorly designed or poorly playing applications, and you may want to introduce commits, for example, to make data sharing work best. But the actual code will continue to work the way it was. Okay, what is a parallel sysplex? Parallel sysplex is made up of a bunch of components, and they allow us to put together a bunch of LPARs. They can be in one box, they can be in multiple boxes. And the keys are, we need a timer. These used to be a separate box called a sysplex timer. Now it's just the hardware talking to, you know, the different pieces of hardware talking to each other to agree what time it is. This is important because if I have two DB2s that are writing log records, and I end up with a problem and I have to do a recovery on one DB2, it has to be able to synchronize those log records, so it has to know when they occurred. So all the systems have to agree what time it is. So the sysplex timers are really basic. Then I've got coupling facility LPARs. In my drawings, they're going to be these little triangles. If you were actually to walk into your computer room floor, you would not see any triangles or pyramids. But for some reason, we always made them look like that. These really are just specialized LPARs that are designed to provide fast sharing of memory, because each DB2 has its critical information in its own virtual storage. So if I'm going to have my DB2 share data with Tom's DB2, it's our virtual storage that we have to share. And so we're going to share our virtual storage by using these LPARs up here in the coupling facility. The coupling facility LPARs run coupling facility control code. You can think of that as a pared down operating system. And there are 3 different kinds of structures, which we'll talk about a little bit more. Between the LPARs that are participating and the coupling facilities, we have high-speed links, so they talk to each other. The links have evolved over time. I used to describe what they were made of, but they keep changing. So they might be copper, they might be fiber, they might be back to copper, it might be back to fiber. All of this is defined in a coupling facility management policy. I'm going to call it a CFRM policy. So this policy lives out in the couple data sets, and that's where you define all of your resources. And finally, all of this is run by a part of the operating system called XES, Cross-System Extended Services. Now, there are people who pronounce that as a word, right, says, and when I work with my friendly customers in Brazil, their X has a different value, so they pronounce it Shez. But I never pronounce it that way. I always say XES, because every now and then I'm dyslexic. And if I get dyslexic and then pronounce the word, then everybody won't listen to what I'm saying for the next 5 minutes. The other thing about XES is this is the one that actually talks to the coupling facility. So for the rest of the presentation, I'm just going to lie. I'm going to say that the IRLM talks to the lock structure and that DB2 talks to the group buffer pools. But that's not true. IRLM uses an API into XES. XES goes out and talks to lock structure, gets the result, passes the result back to IRLM. But if I do that every time I talk about it, we'll be here forever. So I'm just going to lie and say that the IRLM talks to the lock structure. From a DB2 point of view, I want to think about what DB2 is doing here as data sharing, and it's going to be a data sharing group. Typically, I'm going to have 2 or more members in a group. The most I've ever seen personally is 22 members, right? I know there are others with quite a number. The fewest I've ever seen is 1. You can have a 1-member data sharing group if you really want to. Each member is going to have its own active and archive logs and be able to read the other members' logs. Or again, if I'm going to run the recovery on my DB2, I need to be able to read Tom's log so I can coordinate the log records. The DB2 catalog and directory and all the user data have to be on a shared disk so we can all get at it. And from a DDF point of view, there's going to be a single location name that represents the whole data sharing group. Ideally, it's the location name you started with before you went into data sharing, because you don't want to change all of your distributed clients out there to suddenly say something different, right? So we're going to ideally use that. And we have ways of coming up with aliases, which we'll cover a little bit later. Within the, once we've set up the data sharing, DB2 is going to use the coupling facilities, and they're going to take advantage of each of those structure types, right? The lock, the cache, and the list. So the lock structure, which I will call the lock structure, or lock 1, there's going to be 1 lock structure per data sharing group, and this little red asterisk that you may or may not be able to see, if I can figure out how to do that, means that that's a required structure. If DB2 cannot allocate that structure, it won't come up. Or if it loses access to it and can't rebuild it, it'll crash. The shared communications area is a list structure, and again, it's a required structure. If DB2 can't allocate it, it won't come up. And then finally, there are multiple group buffer pools. And a group buffer pool is going to be defined for every buffer pool in which I have data that I'm sharing. So at the very basic, today, I'm going to have group buffer pool 0, and 8K0, and 16K0, and 32K, right? Because that's where the catalog and directory do things. And so there, if I have 2 DB2s, we're going to allocate at least those group buffer pools. But I could easily have table spaces in BP1 that I'm sharing and indexes in BP2, so I'll have a GBP1 and a GBP2. Those are not, strictly speaking, required. DB2 won't crash if it can't get to GBP0. It may not do anything interesting, right? You might get a bunch of -904s when you try to do things, but it'll still stay up, okay? The shared communication area is what DB2 master goes after, right? The system services address space. Again, it's a required structure. If I want to rebuild the structure, if I want to move it from one CF to another CF, all the DB2s cooperate to make that happen. But it's a bunch of group-wide status and exception information, including things like the logs and the bootstraps, and it's generally not a performance concern. In the mid-90s, I cared a lot because we were shoehorning everything into an itty-bitty little coupling facility, but nowadays, this is, in the grand scheme of things, this is so small, and the amount of traffic to it is so low that I've not run into a problem with this in years. The lock structure is what IRLM talks to. Again, it's required, and all the IRLMs have to be available to rebuild the lock structure. So if we lose access to the lock structure, or if we're going to move it for maintenance, all the IRLMs cooperate to rebuild it, because the contents of the lock structure just represent what each of the IRLMs have in their virtual storage. The size of the lock structure does influence performance of your applications, and the lock structure is made of 2 parts: a lock table, which has little entries just to indicate whether the hash class is shared or exclusive. And then there's a modified lock list where I have a lot more information about update type locks. The reason this is important is if I'm busy updating my salary record, right, and increasing my salary by 50%, you know, this is a silly example. So I'm busy updating my salary, and then for some reason my DB2 crashes, or the LBAR crashes, or someone pulls the plug, or whatever happens. And over on Tom's DB2, we're running, the tax app that's going to go see how much tax I'm supposed to pay. If he doesn't know what just happened, he's going to get the wrong value. So my record is going to be locked while my DB2 is down, and we call that a retained lock. So Tom's process won't be able to touch my record until my DB2 restarts and figures out whether it should commit or abort that change. Obviously, that got aborted. I didn't get a 50% raise, but it makes for a fun example. The only way to release retained locks is to start the DB2 that was effective. This is going to be really important later when we go through the availability scenarios. The locks that we track in the lock structure are two types. There are L locks, which track concurrency. This just says that I can have lots of readers or one writer at a time for a resource. It's the same sort of locking we've had in DB2 from the beginning of time. We just didn't know they were called logical locks or L locks until we invented data sharing. They're the things we've had since version 1, release 1. Physical locks are new with data sharing. They're really not physical per se, but they have to do with things like opening data sets or sharing package sections or things like that. So they track coherency, and the concept here is that if I have a version of data, and Tom has a version of data, and Adrian has a version of the same page, and then I make a change, their versions are now out of date. They're incoherent. So what we're doing with plocks is tracking who's got a copy of whatever it is so that we can make sure they get updated. The other thing that's interesting about plocks is they're negotiable, right? If I'm just doing a lock on a page, and I have an X lock on the page because I'm updating it, and Tom wants to do something on the page, he has to wait until I'm done, end of story. But if it's a P-lock, then we can negotiate. We can say, well, I've got exclusive use. You want shared use? Oh, well, let's work this out, right? We can do that. So here's my simplified lock structure. I have a bunch of entries here in the lock table, and in each of these cases, this DB2 owns this hash class. So DB2 is going to take any resource in the environment and run it through a hashing algorithm. And if you own that hash class, then you have exclusive access to that resource. And then down here are the shared locks, and we just have indicators in the one byte, each bit for one of the members to say, yeah, I'm reading this hash class, I'm reading this hash class. So there are the X locks. And then the modified lock list is where we keep detailed information about those X locks. So it might be the case that this hash class, which is held by DB2B, behind it there's an actual lock on a page in table 2, right? And behind this one there might be an actual lock on page 27. So, and same for DB2A. So if we go through and happen to lose DB2B, or we lose the LPAR or something, it just disappears, we're going to indicate that these locks are retained locks. And we're not going to allow anyone to touch those resources because we don't know the state they were in, right? They might have been getting 50% raises. And we want to find out, right, whether that 50% raise was going to be committed or aborted, so we have to wait until DB2B comes back. Finally, the last structure we want to talk about is the group buffer pools. And again, these are cache structures. DBM1 talks to the group buffer pools. This is about buffer coherency. Again, if I have a copy and Tom has a copy and Tom changes his copy and mine's out of date, I need to get mine up to date. So there are directory entries which track how many people have a copy of the resource. And then there are the data elements, which are the actual pages, right? The 4K, 8K, 16K, 32K pages. By default, we're going to cache the pages that we change. Okay? So I've got a copy of page 13 of Fred. Tom has a copy of page 13 of Fred. When he changes page 13, he's going to push his copy up to the coupling facility, to the group buffer pool, right? And then if I do a get page for page 13 later, I'm going to find out that mine's invalid, and I'm going to go read this copy from the group buffer pool. That's the primary reason for it to be there, right? To track that I have a copy, and for me to get quick access to the new version. Again, size influences performance. If your group buffer pools are too small, your applications won't perform as well as if they're large enough. Once Tom has written that change page out to the group buffer pool, the page in his virtual storage, in his local buffer pool, is stealable. And if he's got a busy DB2, it's going to get stolen right away. So now the latest and greatest version of this page is out in the group buffer pool. Eventually, I need to get it out to disk. That process is called cast out. Because before we do cast out, that may be the only place this page is, we want to protect it. So we want to duplex the group buffer pools. We're going to use user-managed duplexing. So DB2 is going to keep a copy. Whoops, sorry. Back up. DB2 is going to keep a copy in the primary here and another copy of that new page in the secondary. So that if I lose one of the CFs, or I lose one of the group buffer pools, that page is there already, and I don't have to go through a long, expensive recovery process. Duplexing group buffer pools is strongly recommended. Another way to say this is there's no excuse not to duplex group buffer pools. For many years, my now retired colleague had this argument with one very well-known customer, and they didn't want to duplex their group buffer pools because there was a little bit of performance overhead. And there is, right? Far to the right of the decimal point, you'll find a little change if you have group buffer pool duplexing. Then they had a problem. They lost access to the group buffer pool. It took them a long time to go through and read all the copies of the pages, from disk, the old version, and apply the log to all the resources that were in there. And when they had the meeting afterwards and said, well, how do we avoid this sort of lengthy outage in the future? The answer was, we duplex our group buffer pools. I said, oh, and what does that cost? Oh, it's a little bit of performance overhead. Okay, and how soon can we get it done? Well, realistically, 5 minutes. So, okay, while we talk about the problem, you go solve it, right? And we'll figure things out. So, strongly recommended. All of the things we normally use a group buffer pool for, we will do with a primary group buffer pool. And in the secondary copy, all we're going to do is put the change pages and the directory entries that point to those change pages. That's it. And later we'll talk about system-managed duplexing, but this falls under user-managed duplexing. Does that mean you have to do it? No. Db2, from the point of view of Poughkeepsie and the operating system, Db2 is just a user of parallel sysplex services. So Db2 is doing this, and it understands what it's doing while it does it. Question?
Yeah, just with the duplexing, when you go to 11 new function mode, is there one type of duplexing you need to turn off?
Okay, so the question is, if I go to Db2 11 new function mode, do I have to turn off a kind of duplexing? And the only change in duplexing that I'm aware of comes with Db2 12, and it's about system-managed duplexing, so it's going to affect the lock structure in the SCA. And so in version 11, no, you still want to duplex your group buffer pools, and fundamentally that isn't going to change when you go from 10 to 11, whether it's conversion mode or new function mode.
I thought I remembered one in the install, one thing where in new function mode it says if you're duplexing, turn this off while you run this job because it's rebuilding the SCA and it won't work if it's duplexed.
Oh, I see what you're saying is,
I just don't remember which one exactly.
Is if you expand the bootstrap during the migration?
oh, if during the migration you're expanding the bootstrap, then you want to stop group buffer pool duplexing? So it's about the SCA, not the group buffer pool. Okay. Thanks, Adrian. So here's a simplified view of a group buffer pool, right? I've got the actual pages. When I make a change, I write the page out there, and I've got a whole bunch of directory entries. And the directory entries know what the page is and where the page is in my virtual storage, right? It actually has an address for the frame where my page is. And there are 5 of these for every one of these, right? That's the default. You don't have to, you can set it to be 10 or 15, and if you use auto alter, it'll adjust for you. And the secret sauce behind the 5-to-1 ratio is the 80-20 rule, right? 80% of the time I'm reading, 20% I'm writing. If you add 4 and 1, you get 5, right? And that's all it is, right? Just the default 4-to-1. I've seen customers with a ratio of 255-to-1. I've seen some that are down to 1-to-1. That's just the starting point. Again, that's a simplified view. Okay, any questions about the basics? All right, let's talk about some configurations. Generally, we're going to start with non-data sharing. In my example, I've got Db2P as the subsystem, and these are the different address spaces, right? I've shorthanded it, right? So this is Db2P, DBM1, Db2B master, and so on. So I've got these address spaces. My local attach, Kix, IMS, TSO, et cetera, is going to use Db2P. Out in the network, my distributed clients, if they're not using SNA, and I'm not going to talk about SNA today, are going to use the IP address or domain name and a port and a location name. And in this particular case, my port is a loc for a location Db2P. And of course, I've got catalog, directory, user tables, and my recovery log. So when I go to one-way data sharing, I hopefully go through the install panels, and what ends up happening is I'm going to create new procs that are going to behave differently than the old procs. You don't have to change the subsystem name, but I like doing that there. So when I go to one-way data sharing, I'm going to call my member DB2A. I'm going to keep the name DB2P as a group attached name so I don't have to change my batch. I don't have to change kicks, right? They'll still talk to it. They'll say, let me talk to DB2P, and I'll find it because zOS will know, oh, yeah, I can talk to this by calling it DB2P. Out in the network, wherever I put this, must be on the next page. Once I go through this and start DB2 as one-way data sharing, now I need to have access to the SCA and the lock structure, right? So before I do this, I have to talk to whoever owns the CF, right, and the safe RM policy, which is probably the MVS team or the zOS team, perhaps the capacity performance team. So I make sure that they define those structures because I need the SCA and the lock. I might as well have them define the group buffer pools, but I don't need them yet. So then I go through the install panels again and I add a second member. They're each going to use that group attached name of DB2P. So now I can take my batch jobs and I can run them either here or there without change because it's still going to say DB2P and get to one. The other thing I've added now is I've added group buffer pools because now I'm going to be actively sharing data between these two. And I've added DB2B's recovery log. So this is the simplistic view of the way things were, say, in the mid-90s when we started with data sharing. I had two KECs, 2 LPARs, and I had 2 external coupling facilities. I put the lock and the SCA on one, and I balanced the group buffer pools across them, right? And in the mid-90s, we couldn't do duplexing, but later on, once we started doing duplexing, we would just spread the primaries and the secondaries across those two. Later, Poughkeepsie came out and said, you know what? We're going to provide processors with this specialty engine called an integrated coupling facility. We also call it internal coupling facility, or ICF. And we're going to have this live on the same footprint. So we went from 4 machines down to 3, right? So we saved operations issues, power, cooling, all the rest of this. And what we're going to do is we're going to keep the SCA and the lock on the external CF because we want them failure isolated from the RLMs and DB2s. Because remember, if we lose the lock or the SCA, DB2 is going to come down. So with this kind of a situation, I can lose any one box and I haven't lost the data sharing group. Some customers said, well, this was great. I went from 4 down to 3. Can't I go down to 2? Right? Can't I just have 2 machines and have 2 ICFs? So physically you can do that, and then the question is, where do you put the lock and the SCA? Right? If you put them on the left side, and then someone does something silly and you lose that machine on the left, the whole data sharing group goes down, right? So if I lose one complex, what's going to happen? Well, depending on which one it is, I could lose one DB2, or I could lose the whole data sharing group, right? So to get around this, zOS, XES, provided system-managed duplexing. System-managed duplexing is where XES handles all of this, and DB2 knows nothing about it. In system-managed duplexing, XES is going to keep a copy of the SCA on both ICFs and a copy of the lock structure on both ICFs. So I can lose either box, and the data sharing group will stay up. I still have to restart the failed DB2 because I need to release those retained locks. But otherwise, I have better availability. The problem is maintaining 2 copies of the lock structure is expensive, right? Maintaining 2 copies of the SCA may be slightly more expensive, but honestly, I don't care. It just doesn't cost enough to matter. But 2 copies of the lock structure might mean that your host CP per lock request is 3x or 4x what it was before. And if you're doing millions of lock requests per hour, that's going to make a difference. That's if they're next to each other. If you take this and start spreading it out, you know, across the street, across the river, across town, into the next state, depending where you are, every time you go talk to the other structure, you're taking 1 millisecond per kilometer round trip. That's really going to, no, 10 mics. 10 mics per kilometer round trip. That's really going to extend the elapsed time of lock requests. So this works. There are customers who do this today, and they're paying this cost here to maintain those two things. In version 12, M500 or beyond, we have a thing called asynchronous CF duplexing, which greatly reduces the cost of maintaining these two structures, right? And hopefully we'll get a chance to spend some time doing that. Okay, so that's what I call configuration C. Then there's configuration D. I've got 3 boxes, but the way I've set them up is I have a DB2 on 2 of the boxes and an ICF on the 3rd box that has the lock and the SCA. From the point of view of DB2, the lock and the SCA are failure isolated. So the first time I ran into this was with a customer who was based in, at the time it was based in Chicago, and they had this setup. They had 3 CECs, and they had 3 data sharing groups: production, QA, and development. And each one had the lock and the SCA on the 3rd, on the different box. So it didn't matter which box went down, I still had data sharing available in all 3 groups, right? So this might have been production, and we moved this DB2 here, and the lock and the SCA, that would have been QA, and we moved this DB2 and the locks over there, and that would be dev, right? So I can do various things with this configuration. This is just a special case of B, right? It's in effect an external CF even though I'm using ICFs, because I don't put a DB2 where the lock and the SCA are. And then the final thing to think about is parallel sysplex in a box, right? I have a single box, so I'm probably not protected from most of my hardware failures, but I am protected from the vast majority of software issues, right? And I can do IPL, rolling IPLs, and I can roll maintenance into DB2 and whatnot and still keep my applications available. So there are a number of customers who have high availability requirements, but who really don't have the budget to go past 1 frame, right? They don't have the capacity requirement to have 2 frames, and they're just not there yet, but they do want higher availability, so they're going to do parallel sysplex in a box. Now, if the box goes down, there's no availability, but that's where they are today already, right? Already today, if they lose their 1 box, they're down. However, in this case, they could do, zOS IPLs, they could bring in, roll maintenance across their DB2 members, and while they bring down DB2A to put maintenance in, they can run their transactions against DB2B. So any questions about configurations before we go on to the next topic? Yes?
If you don't know what a configuration is, like who would know, or how can you find out specifically?
So the question is, if you don't know which of these configurations matches your environment, how do you figure that out? Yeah. Okay, so the technical answer is there's a bunch of displays that if you have authority to issue the displays, you can gradually find out all of these things. The non-technical answer is that there's probably someone in your environment, either near you or far away, who knows this. The humorous answer is you take coffee and donuts to your zOS team and say, what is the configuration? How is this set up? But I've been told, Lethica isn't here, so I'll pick on her. When she goes to her MVS team to get support for the parallel sysplex and CFs, coffee and donuts isn't sufficient. They're not young enough to want yogurt and a latte or cappuccino, but they insist on a steak dinner, and then they'll give her what she wants. So, but it's a fair question. If you don't know that what the environment in which you're operating, you're going to have to find out who set it up, because if you're the DB2 person, you're going to want to know how this works.
Yeah, I used to work with them, so I know how that works.
Oh.
Just because we have new people come in, and sometimes the people who set stuff up have retired, so they're not part of the migration, so it can be a little dicier. And you're right, somebody should know, but sometimes it's good to know. Like, should you look at the CFR and policy and the group buffer pools, and you just kind of figure out?
So yeah, the fundamental of the concept is if the people who set up the parallel sysplex and Db2 data sharing have retired or won the lottery or whatever and are no longer available to ask, then how do you do this? Well, yes, there are a lot of displays that will tell you all this slowly and methodically. Hopefully someone in your environment keeps a snazzy PowerPoint with all the details and keeps it updated, right? Yeah. All right. Thank you. So let's move on to talk about the issues. So again, I've broken them into performance, availability, and workload balancing. So we'll start with performance. I'll probably spend a fair amount of time here. So the design goal when Poughkeepsie and Silicon Valley Labs were putting together data sharing, the design goal was that there would be hardly any impact if we're not actively sharing data, okay? And that if we start sharing data, that the applications don't have to know, that DB2 will dynamically recognize that it has to do things like allocate group buffer pools, and nobody else is going to have to find out, and DB2 will recognize it on the fly. In addition, if we get to where we're doing active data sharing, we want to have minimal and acceptable overhead. And the vast number of customers that I've worked with who have implemented data sharing proves that it is acceptable, right? Generally speaking, it always varies, but generally speaking, I can take my current workload in one box, and I can run that same workload in two boxes with parallel sysplex and data sharing, and I'm going to take about a 10% hit, roughly. Might be a little bit more, probably going to be a little less. And what I'm getting for that is avoiding planned and unplanned outages, which is probably pretty significant. Once we add the third or the fourth or the fifth, right, the scalability is almost a straight line. Now, to make data sharing work, we have to do those things we talked about earlier, right? We have to have concurrency, which I'll call global locking, or coherency control, managing the change data. So concurrency, again, just says for any one resource, I can have multiple readers or one writer, right? And if Tom and I both want to update my salary record, one of us gets to go first and the other one has to wait. That's basic rules. And then inter-system coherency says, I've got a copy of the new salary record and Tom doesn't. And he's about to do something to it, so he needs the new copy. It's not good enough for him to operate on the old copy, because then we're going to lose my 50% raise. And I would hate to see that happen. So the data sharing I mentioned on the previous chart is about handling the messages that do this. And there can be a lot of messages. My personal record that I've seen on a report is 166,000 synchronous lock requests per second. This was 10 years ago in a three-way data sharing environment, so the technology was much older, and they were screaming. I mean, it was working beautifully even at this number of messages per second. One of the things to think about, and this goes into what I talked about with system-managed duplexing, the lock and the SCA and the group buffer pool, most of those messages are synchronous. And when I say synchronous, what I really mean is that the host CP that starts that request is busy for the duration of the request, right? So when my application wants a lock, DB2 says to RLM, go get this lock, and the RLM says to XES, I want this lock. XES is going to get started, and so there's a processor that's doing this. And that processor is going to load the link buffer, the message is going to travel out the link to the lock structure, the lock structure is going to figure out the result, pass the message back, and hand it back to the processor, which was doing nothing else that entire time, just waiting for the answer, right? We used to call it dwell, then we had to admit that it's actually spinning. So this processor is busy for the duration. That's important, right? If it takes a long time for that lock request to come back, that means that host CP is busy a long time. And if it's busy a long time, that means your monthly 4-hour rolling average goes up, right? So we care about the fact that almost all of these requests are synchronous. So we like it when we can keep the lock structure nearby, 7 meters or whatever it is ideal. But some customers do it a kilometer apart, right? And it still works, just costs a little different. So the kinds of things that build in the cost of overhead depends, and these are all the things it depends on, right? Your hardware configuration, how much locking you're actually doing, how much time is in DB2 and not in DB2, you know, how often you need to get a lock, how often you're actually sharing data, the release of DB2, right? So there's all these things that figure into it. And I would say when you go from non-data sharing to two-way data sharing, my argument would be, here's the box of all my work, it's X. I now have two boxes doing the same amount of work, it's 1.1X, right? Individual address spaces aren't going to match this, right? The IRLM is going to go from hardly busy at all to ridiculously busy. But if you stack all the address spaces by, you know, CPU consumption, the IRLM is going to go from way down here to almost way down here, right? You're not going to notice it. But overall, right, there's going to be a lot of things going on that's going to drive your overall up 10% for planning purposes. And then another 0.5% as you add third, fourth, fifth, sixth member. What I really like for performance is have balanced configuration. A balanced configuration means my host CP is the same technology as my CF CP, right? That's the best. There are some customers where the CF is one generation behind. It works, but that likely means that that host request, when the CP is busy, it's going to wait a little bit longer because that slightly older, slightly slower CF is getting back to it. If you make the, you also want to have plenty of links. If you run out of links, that's going to have all sorts of problems. And you want to make sure you have dedicated engines in production. I like two, right? You get way more engine availability if you have two engines, right? You can run two engines at 30% busy because that means you're 100% busy only 9% of the time, right? So I like having two engines. So the issues I've run across over the years, the CFs aren't big enough. The CFs were too slow. There was lots of heavy update, and group buffer pool cache that wasn't keeping up. Closing data sets too often, going out of group buffer pool dependency and into group buffer pool dependency back and forth and back and forth. Each one of those takes sort of what we used to call a hiccup, right? It would cause things to slow down temporarily. And of course, my least favorite is the long-running unit of work. Right? This is the batch job. Nobody has one of these, right? This is the batch job that runs for an hour and a half without taking a commit, right? Nobody has one of those, right? You fixed them all last week. Good. So I've got more details about each of those on the next few slides, but I'm just going to cover a couple highlights here, right? If I don't have enough CPU in the CF, I don't have enough engines, then the CF is going to be busy most of the time, and the host CP is going to be waiting longer to get the results back. If the host CP waits longer, that's more expensive. Your monthly 4-hour rolling average goes up. If my structures are too small, I can have similar effects, right? I can have more false contention. False contention is where two different lock requests go to the same hash class, so it looks like contention, even though I'm looking for tablespace Fred, page 13, and Tom's looking for tablespace Wilma, page 27, right? They're completely different resources, but when you go through the hashing algorithm, they end up at the same hash class. And if my lock structure is too small, I only have a few hash classes, and we're going to collide all the time. Now, XES recognizes that right away and says, hey, that's not real contention, that's false contention. And then XES says, hey, you two IRLMs, work it out. So you two IRLMs work it out, that means overhead, right? If the group buffer pools, and if you don't have enough modify lock list entries, right? If you don't have enough of those, then the IRLM will slow down. In some cases, it'll actually come to a stop because it's full of things that are being held. And you remember that hour-and-a-half long job that wasn't committing? All of those update lock requests are sitting in there, and they're not going anywhere until it commits. And if it fills up, IRLM won't be able to do anything more.
Question?
Yes?
Are there metrics for this?
I'm sorry? Are there metrics? Yeah, okay, so the question is, are there metrics for false contention and for the modify lock list entries? The second one, yes. So false contention, you can see lots of places, statistics log or on the CF activity report. And the modify lock list entries, you're going to see how many entries you have in a display group. That'll tell you how many entries there are. You're going to see how many of them are in use in a CF activity report.
That's a snapshot at the end of the interval.
The snapshot, it's an average over the course of the interval, right?
No, it is a snapshot.
I'm sorry, you're saying the number in the CF activity report is a snapshot. Yes, that's true. which means you're only getting that picture at that moment in time, so you don't know what it looked like in between. Correct. Usually you're going to find it if you get a message saying RLM is slowing down.
Oh, so there is a...
Oh, yes. If you start running out of space, you will get a message. The problem is you probably don't have automation set up to cover it. Typically, the modify lock list is half of the lock structure. That's the default. The only time that's an issue is if you're running SAP, right? SAP takes lots of row-level locks and doesn't commit. So in SAP shops, you build the hash table this big, and you put the modify lock list this big. And you just have to go through and do that. It's not by default. If your group buffer pools are too small, you won't have enough directory entries to track all your changed pages, and that means that the pages in your local buffer pools get marked invalid when they shouldn't be. So you end up doing extra IOs that you shouldn't have to do, right? Also, if the group buffer pools are too small, you may encounter a situation where Tom is trying to write his pages to the group buffer pool and cannot. And if he cannot, then he'll keep trying and keep trying and keep trying, so that's overhead. And if he still can't, then we'll put those pages on the logical page list, and then I can't read them, right? Nor can he, until we go through and do recovery. So we don't want the structures to be too small either. Unbalanced host, again, if the CF is too slow, then the host pays too much money. If the CF is faster, that's great. One of the things that happens is if it takes too long to get a request back, XCS will change from a synchronous request to an asynchronous request. Right, we call this the heuristic algorithm. The good news is that my host CP can go do other things, right? The bad news is it takes longer for the lock request to come back, and we're really not saving that much CPU overall. So I talked about if we're updating heavily but not casting out, then we're going to fill up the group buffer pools. So we want to make sure that we keep the vertical deferred write set down so we're getting steady writes to the group buffer pools, and keep the group buffer pool thresholds so we have steady cast out going on so we don't get too many spikes. And then if we do lots of open and close, that means we go into and out of group buffer pool dependency. And anytime we go into group buffer pool dependency, we go through PLOC negotiation, and we suddenly have to find out everything that you've been doing, and I've got to tell you everything I've been doing, and all of that is you know, overhead. Once you get into group buffer pool dependency, if you're likely to be there for a while, it's better to stay there instead of flip-flopping in and out. And then I already mentioned the long-running units of work. Not only do they have impacts to lock avoidance, but they have impacts to recovery, right? This hour and a half long batch job that doesn't commit, if it ab ends at 1 hour and 29 minutes, right, then the odds are it's going to take 3 hours to back out, and the people who've been waiting patiently to get those resources for 1 hour and a half now waiting forever. So yeah, there are lots of issues there. So any questions on performance before I sprint through availability? So again, the design goal is to have 2 of everything. And these days you can even have 2 disks, right? Because you can have hyperswap. So if we have 2 of everything, then I can lose any one thing and I can still keep my environment going. One of the things here is, to make this really work, you need to automate recovery. The example Lethika gave yesterday, if the operator is out to lunch and you can't get something done until they get back, that's a problem, right? So we want to make sure that we have automated recovery for when we do end up in a failure situation. So if I look at the overall Sysplex, I've got a bunch of different resources here, right? I've got clients out there, I've got my transaction managers or my batch jobs, I've got the apps themselves, DB2 and the LPARs. And so what I'm going to do here is, if I have a planned outage, I just quiesce this DB2, and the other DB2s will handle the work, right? Between DB2 and Kix, I can take advantage of CICS Sysplex Manager, or Kixplex, right, CPSM. And the Kix we routed to another Kix region that's over here talking to this DB2 on this LPAR. So I can take this DB2 out, and everybody keeps working. And then when I've done the maintenance or whatever, and I bring that DB2 back up, then I can start routing work back to it. This works as long as the applications are Sysplex enabled. If your applications have an affinity to something that only exists on this LPAR, then this little model doesn't work. So I can do this for a single DB2, and I can do the same approach if I'm doing rolling IPLs or hardware changes, right? I'm not going to do my hardware changes in the middle of the online day, but during a relatively quiet time, I move all my work over here to this hardware, I roll this one out, roll another one in, plug everything in, and then spread it back out again so we get back to our normal picture. Release migration is just a special case of that, right? We're going to end up, taking one member down and bringing it up at the new release level, right? So a bunch of DB211s, take one down, bring them up at DB212, and once he's done catmate, now he's running DB212 code, and the others are running 11, and that works. And then gradually we'll go through each of the others until we get to everyone running version 12. If I have an unplanned outage, the key thing about unplanned outage is I might have retained locks. And whoever that is who is waiting on that retained lock, they're not going to be able to do anything until I restart that DB2. If I lose the LPAR, the impact on the user is going to be about the same, right? There's going to be maybe more users affected, but the people aren't going to be able to get at it until we restart those retained locks. What we don't want to do is wait for an IPL, right? So is this 20 after 3 in the morning, or is it 20 after 3 in the afternoon, right? Doesn't matter, does it? But at some point, if it's 20 after 3 in the morning, you got a whole bunch of people waiting to do things. We're waiting for one person to say, yeah, IPL the system. And if you wait for an IPL and someone doesn't decide right away to do the IPL, then you have a bunch of people waiting on those retained locks. And there's a whole bunch of war stories that we can tell you about situations where they have not automated the restart of the failed DB2. So as soon as you lose an LPAR, you restart that DB2 somewhere that has access to the coupling facility so he can come up, release his retained locks, and then everybody can get back to work. For coupling facilities, if we have a planned or unplanned outage from the CF, we can be able to rebuild those structures over to the other CF. So all of the DB2 members, the master address spaces, will rebuild the SCA. All of the IRLMs will help rebuild the lock structure, and we build them into space that's been left for them on the other CF. If we're doing it planned, there are some commands to move the structures back and forth in an organized fashion. If it's unplanned, as long as the IRLM and the DB2 are available, they can do the rebuild. So common issues are relying on manual restart and that emergency bridge call. So I already gave you one of those examples, right? Waiting to start that DB2 to release the retained locks. Another one is where you have a 2-KEC configuration and you're not doing system managed duplexing, right? So I've got 2 KECs, 2 ICFs, and you decided not to duplex the lock in the SCA. And then what happens? Well, someone drives the forklift through the loading dock and spears this machine where the lock and the SCA were. And the whole data sharing group is out, right? There's no application access to data at that point. You think that's a silly scenario? Yeah, well, all the ones I come up with are ones that people have told me about, either that I've been there for or people have told me about. So we want to avoid that. People I already told you that don't implement group buffer pool duplexing, right? People who've done that have paid for it. If all of your applications only exist in one LPAR and you can't route around failures, you can't run those applications on other LPARs, then you miss all the availability benefits. And again, long-running units of recovery because it takes a while to get the service restored. So this is just detail for each one of those. And I've already been through this example, right? If I'm in a 2-KEC configuration, I want to duplex the lock in the SCA for highest availability. Otherwise, I'm just taking my chances. Okay, questions on availability before we talk about workload balancing. Okay, so workload balancing, again, I have all of these resources here. The vast majority of them are available as a group, right? I've got a single DDF location. So as someone out in the network here can, whoops, someone out in the, wow. There we go. I've got a single network name here, so anyone out here can get to any of my DB2s using a single location name. I can also use a location alias to subset them. Let's say that these 2 DB2s are my protected, high transaction DB2s, and I have some users out here who haven't quite completed SQL 101 training and don't know how to write a join, right? I don't want them showing up here and consuming all the resource. So I might tell them that they can use an alias that only points to these two members over here. And maybe it'll perform differently, but at least if they do something silly, it won't affect my major operations. So I can do things like that. I have the group attach name, right? Everybody knows about every my DB2s by Db2P, but I can also do subgroup attach. So I can have batch that will only be able to run on these two DB2s, right? Because I have a different subgroup attach, you know, DB2F or DB2G or something like that, that's only specific to those. Things that have group scope include things like displays and performance monitors, DDL bind and utilities, right? If I'm doing DDL on one member, whatever I'm doing is going to affect everybody else, right? If I alter a table, I need to have a lock on that table. And then if I'm running WLM stored procedure address spaces, right? These are the external stored procedure address spaces. I want to specify those application environments with a symbolic, so that way I can have the same application environment that runs on any of my DB2s. Most of what's going to go on in workload balancing is managed because all of these different components that are running in your environment are going to cooperate, right? Workload manager is going to keep track of what DB2's health is. Kix plus systems manager can route around failures because it knows what transactions need to run where, and it can identify when a CICS is having a problem. IMS transaction manager can do shared queues, so again, we can route the work around. WebSphere that's running on Z, if you want to do this, you're going to have two WebSpheres. That's why I have several WebSphere boxes here, right? One on this LPAR and one on this LPAR, so I can then route my work around. If it's WebSphere off of Z, then I'm going to use DDF to spread the work. And DDF, ideally what I'm going to use is dVipa and Sysplex distributor to spread this out. So I can move all this stuff around. Here's an example, right, with an off-Z WebSphere, right? I've got my logical connections and I've got my transport. So whenever I talk to DDF people, I have to be very careful. Because when I think of connections, I think of those resources in the DDF environment, right? The DAST address space, the things that count up to conDBAT. When people out here think of connections, they're thinking of these. And when they're thinking of DDF, they're thinking of transports. So the idea here is that across this little dotted line, these connections can attach to the transport 1 or transport 2 on a commit boundary, so they can take advantage of the fact that they're getting better performance on B than A, and they can bounce back and forth between them. So some of the issues are, if I do have multiple members that I'm trying to route my work to, what happens if some of the traffic gets stuck on one DB2? And occasionally this has happened. So starting in 10, we introduced these two ZPARMs, which will say, if you wait a certain amount of time, or if there are so many waiters in the queue, then we're going to close that socket, and that'll cause the distributed client to redrive and attach to another DB2. If we have runaway requesters, right, and there's a bunch of scenarios where this might happen, you can think of it as a denial of service attack, right? Or you could say maybe someone wrote a silly program that said, open a socket, get a thread, select asterisk from everything. Oh, it's not what I wanted. Okay, open a socket, get a thread, select asterisk from everything. Oh, that's not what I wanted. Open a socket. You notice I never said close socket, right? So if you have something written that way, it can take all the sockets that you have available here, right? This has been done. I know a customer to whom it happened. They, in effect, did it to themselves. So one of the ways to handle that is using system profile monitoring, which is available starting in version 10 and keeps getting enhanced. So you can actually come down and say, for this set of my DDF clients, I'm only going to give them this many connections, leaving the rest of my connections for other people. Question?
What's a DBAT?
A DBAT is a database access thread. That is the thread in DB2 that corresponds to a distributed request. So if you're out there working on a PC or on a Java client and you're coming in, when you actually run in DB2, you're using a DBAT. So max DBAT is the maximum number of active these that I can have, and conDBAT is how many connections I can have that support them. So theoretically, all of us could have connections, so however many this is, and my DB2 could make everybody happen maybe with 12 active, even though we all have connections. depending on who's hitting enter when. Another issue is some customers think that workload balancing means 50-50 or 33-33-33, right? They want workload balancing to mean that everything is exactly even. And really what we intend workload balancing for is we want to make sure that you get access to the data. And if we're starting having spikes over here, we can give you access over there. So we don't anticipate 50-50, right? So when we say, in fact, Adrian likes to use workload management as opposed to workload balancing, right? Is that your preferred term? And then finally, one of the things that some people do is they use what I call penalty box, right? There's a particular piece of software that's really expensive. And if I put it on a teeny tiny little environment, then I only pay a little bit of money for it. And all the work that uses that software has to run there. So the advantage is, okay, I can still do it, and I'm paying less money. The disadvantage is if I lose this box, then I have no availability for whatever that workload is. So any questions on workload balancing? Okay, so I have the summary here. Basically, data sharing is great. I love it. I can talk about it for hours. Of course, you all would fall asleep, and we wouldn't want that to happen. Customers have been running in production since the mid-90s, and new customers are coming to data sharing even as we speak. And we keep putting new new features and functions in the product to support data sharing. From here on out, I don't know, this is probably time that's going to go zipping on through the rest of this, but there's a bunch of resources back here that you can look at. So thank you very much for your attention and for your questions, and enjoy the rest of your conference, and don't forget to submit your session evaluations.
Because we share. Because we share.